The floor is yours.
Okay. Hello, everyone. My name is Jafari. I am a PhD student from School of Electrical Engineering from SBUK University. Today, I'll be presenting my research area that was condition monitoring of industrial system based on hidden Markov model and generative adversarial network under supervision of Professor Maghfoori. Okay, the main idea is about online condition monitoring. For the all industrial system, we could use online condition monitoring. First, we need to install proper sensors into the critical point of the industrial system, and then we can have timely maintenance and avoiding cost of a breakdown. And challenge we most have in the industrial condition monitoring system is uncertainty in the sensor readings and insufficient amount of defect data, especially about rare failure events. So to address this challenge, we have a hybrid models for online condition monitoring. First, we use a generative adversarial network, or for short GAN, for static fault data, and then we use the generated data in hidden Markov model for condition predictions. So first we have a system of we have a hydraulic systems. This is the system. This is a benchmark. I use it from. I use the data from a hydraulic system, hydraulic test rig, and the sensor data was in the system was, for example, temperature, pressure, flow, and other sensors. And we wanted to predict maintenance models, use predictive maintenance models for prediction of the condition of this hydraulic system. And then after the system, we go to rail systems. So this is a hydraulic system. We have hydraulic power supplies, and by this power supply, we have a fluid, for example, oil, that come through hydraulic cylinder and create movements. So we have some, for example, switching valve, SV1 and SV2, and proportional valves for making the flow in a proportional value. And then we have a cylinder for movement up and down. The components in the system that we wanted to monitor. First component is cooler. The cooler keeps the temperature in a safe operating by removing excess heats, and the fault in this component could be reduced cooling efficiency from 100% to, for example, 3%. That is near the failures. The other component is a valve component. The valve is for control the value of flow into the desired actuators, and the fault in this component could be switching delays. For example, if the valve open by delays or closed by delays, and for example, if we have a valve sticking, this could be a fault in this component. Another component is a pump, that is the power source, and it pressurizes the fluid and can drives our movements. The fault in this component is it could be internal leakage in the pump. So we have less fluid, then this is the kind of fault in the pump. And another component is a accumulator that stores hydraulic energy under pressure. And the fault in this component can be pressure loss. For example, less energy is stored, and the system becomes unstable under sudden loss. And the sensors in this system are pressure sensors. We have 6 pressure sensors that measure in bar at 100 Hertz sampling rate. The motor power sensor measured in watts at 100 hertz. The volume flow sensors, FS1 and FS2, there's two sensor measured in liter per minute at 10 hertz, and the temperature sensors, four temperature sensors in degrees Celsius at 1 hertz and one vibration sensor. The conditions indicate, there are some conditions in this system. We have indicators of each condition. For example, for cooler component, we have three conditions. The first is close to total failure. We show it by 3. The reduced efficiency, we show it by 20, and full efficiency, it's 100. Another component is pump, that we have internal pump leakage. For example, for the state no leakage, we have 0. For state weak leakage, we have 1. And for state severe leakage, we have 2. And for valve condition, also we have a 4 condition: optimal switching behavior, a small lag, severe lag, and or close to total failure. And also another conditions for hybrid accumulator is 4 condition: optimal pressure, slightly reduced pressure, severely reduced pressure, and close to total failure for the accumulator. And there is another an overall indicator for condition of the system is a stability flag. We have 0 for condition, a stable condition, and we have 1 for a static condition might have been reduced here, might not have been reduced. And the problem in context is we have 4 problems. The first one is rare failure data. In industrial system, we mostly have a challenge with the rare failure data, because usually the systems are working on normal operations. So we have the a scarce number of labeled failure examples. And another thing is uncertainty. For example, in the hydraulic systems, we could have sensor noise, we could have environmental fluctuations, and but the true state of the system, for example, healthy or faulty, is hidden. We couldn't directly observe the state of the system. So, for challenging, address the first challenge, that is the rare number of the defect data or insufficient data. I propose the generative adversarial network, or GAN for short. GAN consists of 2 neural networks. The first one is generator, and the second one is a discriminator. Generator starts with the latent space using noise, input noise, and generate data that we name that data as fake data. And then the fake data goes as input to the discriminator, and another input for discriminator is the real data. So we have a real and fake data as input of discriminator neural network, and then discriminator labeled the data as real or fake. So for the real data, it's labeled the real, and the fake data, the initiated fake data, it labels fake. But after some training process, the generators train how to generate data that is very close to real data. A discriminator cannot distinguish between fake data and real data. So the discriminator then labels the fake data as the real data. That means the fake data is the distribution of real data, fake data is very close to real data. So by this network, we can produce the defect data, sufficient defect data. For the first, I use a standard GAN. The standard GAN has 2 generator that's used with a noise vector, a probability of a noise vector, and generates static data, and a discriminator outputs the probability of input of real or fake data from the generator. And we have the minimize objective for the standard GAN. This is the last function of GAN. Try to minimum the ability of a discriminator. I'm sorry, maximize the ability of discriminator, and generator tries to minimize the ability of discriminators. So I generated the data by this standard GAN, but we have a problem. We have mode collapse by this standard GAN. For you can see here, the dash line is the GAN outputs. And you can see in the dash line we have a variety of the data. The data generated by a standard GAN is doesn't have variety and doesn't close to real data. So we try another GAN that means name is Wasserstein GAN. The Wasserstein GAN uses the Wasserstein distance or Earth mover distance, another name, to measure how a difference to probability of real data and fake data are. So the Wasserstein GAN uses a generator like the standard GAN, but it has a critic instead of discriminator. The critic scores the output, scores the data output from generator, not labeled, just real and fake. It scores them from 0 to 1. That means how the generated data, how is close to real data or not, by the score, not by just label. So the Wasserstein distance, we have two probability distribution, real data probability and generated data probability. And the Wasserstein try to minimum cost of transportation probability. If we have a joint distribution, for example, gamma of x and yx is the data, real data, and y is the generated data by GAN. And also we have a probability of real and generated data. The Wasserstein data is like infimum of expectation of norm of x minus 1. And the last function of WGAN is tries to score the generated data for fake and between real and fake. We have B for critic that scores the real samples, and we have G for generated data generated from noise. And the critic aims to maximize this difference, and it gives a high value to the generated data, to the, real data, and low value to the fake or generated data. So when I uses this WGAN for creating the data, you can see here that the results are much better than a standard GAN. We don't have a mode collapse here. The accuracy of the generated data are very high, and the generated data by WGAN is so much better than a standard GAN. After generating the data, the fake data, we could use a hidden Markov model for predicting the condition of the system. Hidden Markov model is a probabilistic model for time series data with hidden states. Here, this is kind of hidden Markov model. The blue circle are observation, and the Z are the hidden states. Here, for example, are the conditions of the system. For example, healthy, degraded, or failure. And since we cannot measure the conditions directly, so we can use hidden Markov model for predicting the conditions. The hidden states in the hierarchy system could be conditions are, for example, each condition of the each component, for example, pump, valve, or another components. And the hidden states can be shown by S1, S2, and another observation. We have an observation that are sensor collected data. And initial state distribution, we use an initial state distributions. And we have a state transition probability matrix that shows how the states transition from one condition to another condition. And also we have emission probability distribution matrix that shows the probability of the being in one condition under the observation. So the model is defined by A, B, and P. The learning parameters for the hidden Markov model, I use a Baumwelt algorithm, that is expectation maximization algorithm. And first we have initial amount of probabilities, and then we re-estimate transition probabilities and re-estimate emission probabilities. And here we have probability of each state, and we have probability of transition between each states. So the result of a hidden Markov model for each component states are good. For example, for the valve condition prediction, we have a little misprediction, and you can see the other component. We have a pump leakage prediction. We have accumulator prediction confusion matrix and a cooler confusion matrix that the result shows a good accuracy. And also, I compare the accuracy of using a hidden Markov model without having a GAN, without augmentation GAN, and the accuracy is much lower than using hidden Markov model and augment data with random noise augmentation, adding random noise to the data. And also hidden Markov model using the standard GAN generated data, and the last one is hidden Markov model using W GAN generated data. And you can see the hidden Markov model plus W GAN has the most accuracy. After that, I go through rail data set, rail condition monitoring. In the rail data, we need to have a continuous monitoring of rail for using for infrastructure useful life remaining, and for reduce the maintenance cost. And the data was acceleration data collection from Tehran subway at Shahid station. The research focused on the Tehran subway, and the acceleration sensor were installed on the line of the stations. We have 3 acceleration sensors here. Data collection was during 9 months, but now stopped the data collection, and the acceleration collection was for 18 hours each day. We have 7 wagon, and also we have 28 wheels. So when each train through a pass. First, I try to use this equation of motion for the flat modeling, and I add the flat model here in this equation of motion. The result wasn't so good, so I didn't bring it here. And then I try to consider roughness in the model, and I just started to modeling roughness, so I don't have the result for now, but I try to considering roughness and modeling the defects, and after wheel flat defect, I want to try other defect modeling and collecting the defect data. And after that, I can use the GAN and hidden Markov model for this data set. And the next step, I don't work on it, but this is in my mind, to using a physics-informed deep hidden Markov model for if we don't have complete defect data. So I thought about Maybe I can use the physics inform and physics inform deep hidden Markov model. As I said, as I saw that there is a deep Markov model for now. But if we could use the physics constraint, for example, for the hydraulic system pressure dynamic, valve switching delay, or pump suffer laws, and combine it with deep neural networks to learn emission function or generate latent feature from sensor data. Then we could have a big supervision or partial labels, so for generalize even without complete failure data. And this is how we can use a deep neural network and physics equations, combine it with hidden Markov model for reduce overfitting to noise, and combine physical truth with data-driven learning. And we can handle missing or rail fault data. So that